Dr. Rajesh Ranganathan. So that much amount of work he has given for this additive manufacturing community. He's a dynamic self-starter with a lot of research potential. He's an excellent team leader. And about himself, he received his studentship from Loughborough University, UK, where he has pursued his PhD in Wolfson School of Mechanical and Manufacturing Engineering. He is a recipient of Young Scientist Award from DST India, and believe me, he has obtained a funding of rupees 9.32 crores from Ministry of Human Resources and Development for establishing Center of Excellence in Manufacturing Science in CAT. And he is a recipient of ESQR Quality Achievement Award, where he has received his award in ESQR convention held in London in 2015. He has got his PhD in manufacturing management from Loughborough University in UK, and he has obtained his master's degree from Coimbatore Institute of Technology, India. And he has served in Hyderabad and University of Aberdeen, UK, where he has served as Knowledge Transfer Partners Associate for a period of 8 months. And right from 2009 to till date, he is working as a professor in Coimbatore Institute of Technology, India. He is involved in knowledge transfer activities, and he is involved in educating, communicating through lecture the experience obtained in the area of supply chain management and additive manufacturing. And he's guided about 10 PhD research scholars in the area of logistics, inventory management, strategic planning, and additive manufacturing. He has worked as a placement officer, staff advisor of Trade Club and Mechanical Association, and he is serving as a director, Center for Excellence in Manufacturing Science, which is the MHRD sponsored Center of Excellence. And he has worked as center head. He is involved in undergoing consultancy for industries and hospitals in the areas of manufacturing. And he has about managed 5 research associates and handled about 5 different research projects. And he is involved in periodic reporting and presenting the outcomes during the progress period to MHRD. And he has worked in KATP Associate, Hyderabad University of Aberdeen, UK. And he has got different subjects in mechanical engineering discipline. And he has got a wider network within home and cross-country academicians in multidisciplinary subjects. And he has completed a project from MHRD Government of India, that is a topic advanced training and research center of excellence in manufacturing sciences by incorporating rapid prototyping and rapid manufacturing technologies. And another project he has completed through DST for design and development of innovative product for reduction of food ulcer for diabetic. And he has completed another project for DST, that's haptic devices and toolkits for Geomagic Touch. So another project for 64 lakhs he has completed to DST, that's a development and evaluation of a personalized advanced system for managing pest and disease of potato needles using information and communication technology. And he has got 2 Indian patent filed and 2 US patent filed. And he has published a book, it's a very famous book. It's a Dr. Müller E.K. published in Germany. And the title book is Rapid Manufacturing as an Enabled Technology in Supply Chain Management. And he has published a lot of international journals, a lot of programs he has organized. And his core skills in the area of technology forecasting, multi-criteria, multi-attribute decision analysis. And he's conversant with the problem solving, hypothetical situation, less problem sensing situation. And more important, his experience as a technical consultant, not only as academician. As academician, we need to really cater to the needs of the industries, and that's why we are organizing this program on this Industry 4.2 as a 3D printing for the Indian industries. He has guided a lot of UG projects and PG projects, and is the active player in Center of Excellence in Manufacturing Sciences, where they have done a lot of consultancy projects to industries as well as to institutes. So with these few words, I welcome a man of dedication, the right person to talk in this STTP, Dr. Rajesh Ranganathan. Now floor is open to you, sir.
Thank you, sir. I don't know whether I deserve your such a boastful introduction. Thank you, sir. I feel still I need to go miles ahead. Anyways, thanks very much for your motivating talk, sir. And very good morning to one and all. I thank the organizers, the team for their coordination in getting things sorted. I do understand how difficult to do or organize such an event at this moment, and I really thank them for the work that they are putting in, and thanks once again for your time and efforts. So, having said that, today I'll be handling two sessions. Um, it's more of how we are using additive manufacturing for our perspective. Like whenever you hear about additive manufacturing applications, like I have seen these. I do interact with the sellers very frequently, all the additive manufacturing machines, and when they tend to show some case studies or any applications, the first thing that I tend to ask them is, don't you have any application which you can show to us, um, which it says that this is made by some Indian company or some Indian institute? Why is that you always project something in German? They have did this in UK. They have did this in US. Additive market is like this, and these are the products that they are doing. So then they tend to give a feedback. So we are still growing. So so those are those are times where I think we have the potential, but we haven't used it. So that's all I used to say them. And so soon, I wish there will be a day where when they speak of additive manufacturing within India, they they will be discussing about the case studies which we Indians tend to develop on this. So to that note, like today, I would like to share um, a topic of an application of additive manufacturing for Indian societal use, because you take any product that we are using, it's all developed for a different ethnography, and that was shared by us. Let's say, for example, even the very simple paracetamol tablet, Crocin. Crocin for Indians, the formula for Crocin was developed for UK, and then all they did is they said that okay, in UK the average weight of a person is about 70 kilos. So in that case, we will design this medicine Crocin for an average weight of 70, and then let it get distributed to other countries. So that's how they framed it. And when it came to India, they had a limitation in terms of weight, and they felt Crocin was not working for Indians. And I was because this is, if you just do a Google search for this case study, you would find it. And then they said that okay, we'll just multiply it by two, the dosage by two, and that would suit the Indian needs or the Asian community needs. It was quite surprising. Like, why is that you don't design a product for one specific society or one specific ethnography, wherein all we do is we get something from some other country and we tend to use it. So that's how the product, not only with Crocin, you take any products from shoes to dresses, it's all the basic design is for some other country and we are sharing it. In spite of our technological developments, still we are sharing it. So these are a couple of things which triggered me to think like, why can't we develop the products which are specifically suitable for our requirement, or the products that which we can design for our requirements. So those are some triggering points which make me to think on these dimensions. And today I'll share with you with some of the case examples or how we have went in terms of developing the products which is focused specifically for our Indian societal use. So to start with the basics, we all know about subtractive manufacturing and additive manufacturing. Like if you are taking a bulk of material, and from that bulk, if you are trying to take one segment of or whatever you're looking at, then it is called as subtractive. And whereas the other side, wherein you have the raw material in a liquid form, a metal form, or a semi-solid form, um, and from that source of raw material, if we are trying to build a, a part or a product, then it is called as additive manufacturing, wherein we are speaking of lesser wastage, lesser power consumption, uh, lesser wastage of entire resource. When I mean lesser wastage of entire resource, like here, in order to take this, make this bulk of a product, like we take the raw material from scrap. We tend to put our energy and resources as named as foundry, and then from there we take the bulk of it. Already good amount of energy is spent over there, and when we are spending energy, we do pollute the environment at one hand, and then once the foundry is done with the basic product, that becomes as a raw material. Then here we subtract it by the name machining, and after subtracting it, we leave some scrap out, and again from there we tend to make this part. When we are making this part, we are spending energy while subtracting as well. Whereas on the other hand, when it comes to additive manufacturing, comparatively we spend lesser amount of energy while we are making the raw material, and way lesser amount of energy is spent in terms of making the product. And once the product is done, then it is directly taken for application. So additive manufacturing, though it seems expensive to start with, but the amount of pollution that it creates, or the impact that creates on the environment, is comparatively less as compared to the traditional subtractive manufacturing. So with that lighter note, we know what subtractive manufacturing is, and additive manufacturing, wherein here we add layer over layer in order to make a final end product. The bulk product is taken for application. Here, this additive manufacturing is categorized based on the raw material type. As I mentioned, solid powder form, or a filament form, or in terms of liquid form, or semi-solid form. These are the three major sources of raw materials which are used in this particular technology. And based on the raw materials, the major machines are classified um, into five different categories. And of the five, we widely use four different types of machines. With that lighter note, in our perspective, what we do as a researchers, we take two major areas. One is the supply chain, and the other one is additive manufacturing. When I mean supply chain, I do integrate IT into it. So IT integrated supply chain and additive manufacturing. So combining these two wide arenas, we can't explore in all the areas. So we specifically explore in certain areas how we can reduce the cost of a product, how we can reduce inventory, how we can reduce the lead time of manufacture, how can we be responsive to the customers. On the other hand, when it comes to the additive manufacturing perspective, it is like how better we do customization, how better we can improve the accuracy of the part, and how we can reduce the manufacturing lead time, and how better we provide or develop complex profile parts or intricate parts which was not possible through traditional manufacturing. So those are the wide areas that we look in, and combining these two, we can look into multiple number of product lines, or within the seven wide variety of product groupings. Of the seven wide group, we only look in one group of products, namely the healthcare. Healthcare is our major focus, and we focus specifically on the healthcare side. For this, we do use FDM at instances, but one of the machine that we use is a polyjet printing technology. So, wherein in terms of polyjet printing technology, it uses a liquid form of raw material. And one major advantage of this polyjet technology is, I would say, it is a combination of an SLS and an SLA and a 3D printer. So as a 3D printer, you can print colorful products within a certain range. As an SLA, you can print very complex products which we think we can only print in an SLA machine. And in terms of SLS, again, complex support structures or complex products can also be printed using this technology. So
Sir,
that's why, yeah,
Rajesh sir.
yes, sir.
Uh, Sorry for the interruption, sir. Sir, are you
No,
changing your slides, sir?
yes, sir. I'm changing the
But
slides.
we couldn't able to see the slide change.
Oh, okay. 1 minute, sir. Are you able to see the slide now, sir?
Yes, sir. But at the slideshow mode, we can't able to see the changing of the slides.
Oh, okay, sir. Okay, sir. In that case, I'll just leave it in this mode. Uh, is this fine, sir?
Or else you just share your entire screen, sir.
Yes, I have shared the entire screen.
Yes, sir, now we can see polyjet printing technology. Is it correct,
Okay.
sir?
Yes, sir.
Okay, sir.
Okay, sir. So I'll just leave as such, rather going for the entire slideshow. Is that fine, sir?
Yes, sir.
Yeah,
Yes, sir.
okay, sir. It is
Okay.
fine, sir.
Okay. So we use polyjet technology. One thing with polyjet is, or in terms of SLA, we can only print transparent parts, and if we want solid parts, we need to go for SLS or any or FDM or any other technology. But one advantage with polyjet is we can print a combination of these two, as I said. So that is why I have shown this as an example. You can print transparent parts, and along with that you can also print hard ABS parts. One major advantage with this particular technology is we can also print rubber-like parts, because if not this technology, the only option that we have is we need to print rubber-like parts in a separate manner, and after printing it, we need to glue it together with the actual component. Whereas using this technology, we can print all these combinations in one single go. So that was one of the major advantage of this particular application, and that's why we are using it. You'll have a better idea where, when I start discussing about case studies, you will know where we tend to use this particular one. So ideally, it uses one primary material, one secondary material. Let us say I want a primary material will be a ABS. ABS would be a primary material, and secondary material would be a rubbery material, let's say. So in that case, this the hard material and the rubbery material, or the material with flexible material property, like these two can combine together, and this forms a type called as digital material, wherein we don't need to do anything. The machine by itself tend to make a combination. Say for example, if you want to print a part with a show hardness of 40, that is, we want to have it bit elastic, then all we need to do is we need to load the trace with these material spec, a primary material and secondary material, and we need to fix the show hardness as 40. So the output would be an elastic material. Now I don't want the part to be too elastic or too hard, somewhere in the middle. So in that case, I would put a show hardness of 80. So that would give me a range of the specific type, wherein I don't a medium range of elasticity material or elasticity product. So that was one of the major advantage of this particular technology. So we use it for certain applications. Have a short video on that.
Comics uses inkjet printing technology that can jet two materials at the same time. This allows you to produce models containing a whole range of material properties to more accurately represent your final product. Each layer of resin is just 16 microns thick. You can even mix two materials to create a whole selection of properties, such as this material, which is tough enough to simulate ABS-like engineering plastics in applications such as this, or even this, that can do this. With Object's 3D printing technology, you can take your design idea and rapidly transform it into a functioning prototype. And you can do this with all the subtle details of your intended product built in, including the different material properties of assembled goods, such as this part. Multi-material technology is that you can build up to 14 different material properties, textures, and shades into a single part in a single print job. Object has an incredible range of over 60 materials, from rubber to transparent to engineering plastics, with the ability to mix and match various combinations.
Okay, so with that outline on object technology, I have shown a couple of examples. One is the part which we can only print in an stereolithography, the transparent part, the part which is only possible in an SLS, wherein the complex shape and complex profiles which are coming in, and certain parts which can be only printed using a 3D printer, wherein you're looking at colorful combinations, and finally the part wherein you can print a rubbery products. So that's also possible in this technology. So this is where we use this, we picked up this particular technology for our application. And as it has a very wide application, and I mentioned that we specifically work in terms of healthcare. And if you look at healthcare, the products are very wide, and within that wide range, we specifically concentrate on prosthesis. And again, prosthesis is categorized into two types. One is the internal prosthesis, and the other is the external prosthesis, wherein internal prosthesis is anything that you put inside your skin or under the skin. That's called as internal prosthesis. And a couple of examples are like the bone implants or the implants which are used inside the body. So these are internal prosthesis, and external prosthesis are something which we put outside the human body. It's external prosthesis, and much of our work is completely on the external prosthesis, or else I can say we specifically work on the external prosthesis side. We don't put anything internally inside under the skin. So this is a focus of our work. So we'll start with the first discussion of how we used this particular technology for our societal need. We all know the story, like tying the ice and asking to find what this particular animal is. And we all know that different people give different opinions. And there was certain parameter which was happening over here. That is the communication. Your communication was lost. Your sense of hearing was there. Your sense of touch was there, but sense of vision was cut off. And so that is the time that the communication errors started taking place. And yet another thing that we need to understand from this story is like when a person puts just a finger to understand what this animal is, it takes time for him to understand because his point of contact is just a finger or the fingertip. But on the other hand, if he puts the entire set of fingers, he tend to get a different opinion. Again, on the other hand, if he puts the entire palm or the entire hand over the surface of the um, animal, they tend to get a furthermore information on that particular animal. So what is happening over here is when we have a point contact, we are getting a different information. That is when we put just the finger, and when we improve the amount of point contacts, that is putting all the fingers on, we tend to get bit better information. On the other hand, when we put the entire palm, we tend to get furthermore information on that. So that is one thing that I want to communicate through this. And secondly, um, we have communication error which happens when we tend to when we are asked to write straightly on a piece of paper, we can write easily. But on the other hand, when we are asked to look at a mirror or look at a screen, and then if we are asked to write something on the piece of paper, we tend to lose some information because we are not seeing directly what we are touching. Whereas when we are directly writing on a piece of paper, we are seeing what we are touching. But when the moment we start looking at a mirror, there is a communication gap which is happening here. And there is no measure to measure this communication gap. It is not in terms of weight, it is not in terms of length, or it is not in terms of any measurable quantity. So there is no measure to measure this communication gap. But this communication gap at times plays a very crucial role. So with that note, I would like to discuss on this particular work that we went through. We all know that it's an open surgery. So a body is pierced and the doctors see what they are doing, they touch it, they sense it, they see it, and then they are doing it. Okay. On the other hand, we all know about the laparoscopic surgery, wherein the doctors do the surgery, touch it, sense it, but they see it somewhere at a different place. For a simple case example of writing, when we are losing the information, imagine the situation what happens when a laparoscopic surgery is performed. Yes, it needs a lot of practice, that is one, but still, these are very tiny blood vessels or nerves or veins which are running through the body, and a small marginal error can cost a life for a human, or it can also cause some sort of disability to the human. Like I like to share some more pictures. You can see the way how the doctors try to communicate with the patient while they are performing the surgery. You can literally see they are looking at a screen and then they are performing the operation at all cases. From this, it is very clear, like there is a communication gap which is happening when you're performing an operation directly or under a situation where you are doing a laparoscopic surgery. And the only point of communication that they have between the patient and themselves is through this surgical tool which they are using, or it is otherwise called as laparoscopic scalpel, which they are using in order to perform this surgery. And this is a simple picture of a laparoscopic surgical scalpel. And these are some of the scalpels which are used for laparoscopic surgery. And if we look at this surgical tool, it is a point contact. We just put the fingers in, and putting the fingers in, they tend to perform the surgery. But we do have an understanding now. The the more the surface area of contact with the body, the better the information that we will get. But here it is more of a point contact. So you are speaking of lesser amount of communication which is getting passed through. So already there is a communication gap which is happening because the surgeons are not seeing what they are performing in case of laparoscopic surgery. That is number one. And number two is the only communication medium is the laparoscopic scalpel. And that too, the laparoscopic scalpel, there is no complete surface contact. It is only point contact. So there is a very high chance for the information to get missed. And one more important point over here is, if we look at the surgeons, all the surgeons' hands are not the same. One hand might be thick, one might be thin, one might be tender. So the hand profiles are completely different from person to person. And having these varied hand profiles, all they use is one common tool. So for a thin person, the fingers would fit in, but whereas for a thick person, the fingers would stay a bit away, and still he need to perform the surgery over here. So we are speaking of, as we go bit in depth inside, we would understand there is more amount of communication errors that are happening when it comes to a situation of a laparoscopic surgery. So with this basic idea, we did happen to collect some data in terms of surgical errors that tend to happen in terms of laparoscopic surgery. We went through a questionnaire, we tried to collect the data, and you can yourself, you can do a check on this. When you try to contact a person who went through a laparoscopic surgery, when you ask them how they felt after the surgery, um, at least 4 out of 10 people would say that after the surgery they went thin, they went thick, they had some other allied health issues along with that. So they have some issue or other after the laparoscopic surgery. So that falls under the category of surgical errors. And there are certain reasons for surgical errors. One is the communication error, and second one is lack of technical competency or lack of practice. That is not the area that we are touching. We are only touching on the area of communication gap, and also finally the physical and mental strain that the doctors undergo because of this laparoscopic surgery. Because for every surgery the doctors need to stay with the same tool for nearly minimum time is about 2.5 hours. There are situations wherein maximum they go until 7 to 8 hours on one laparoscopic surgery. So on average, roughly it's about 4 hours wherein they are supposed to hold the laparoscopic tool. Like imagine a situation that a person is holding this particular tool continuously for 4 hours. So that leads to physical strain to some extent, and speaking to the laparoscopic surgeons, they said that most of them tend to take brufen or painkillers once the doctors have completed their surgery, because the scalpels are becoming complicated and it is a tedious process to hold those laparoscopic scalpels. So this gives us the idea that there is a wider amount of communication error which is happening, which we can't afford to happen in this particular place, because this is a human that you're working on, and you can't have a error which can occur because of a communication error. So with that idea, we took on this project, and from this case, we know that we need to improve the surface area of contact, because we can't do anything on the other side in terms of reducing the communication errors. But one thing that we can do is we understand from here that once if we improve the surface area of contact, that would reduce the amount of communication error. So what we did is we took this particular scalpel and we decided we'll try to improve the surface area of contact, because now it is only point contact. So our focus is how can we improve the surface area of contact, and that is where we started studying more about the ergonomical factors, which we mechanical engineers we have studied about it, and so we thought we'll explore more into that, and we studied we focused, we brought in ergonomics, and we started exploring about hand anthropometric data, and understanding hand anthropometric data focuses how we can redesign these laparoscopic tools for our requirement. So with that idea, we took the traditional laparoscopic tool, and as it is our policy that we don't do anything which goes inside the skin, we decided to do any modifications. It is going to happen only on the outside side. Nothing is going to happen on this end. Um, uh, One another reason is we need to go for many medical approvals when we go for any product that we put inside the body, whereas working on outside, it's a different scenario. So we decided to work only on the outside perspective, and that is we will be only changing this design than anything else. So we went on a couple of iterations in terms of design, and our idea was like when we start designing this, um, we will use the same mechanism. If at any point of time, if the surgeon is not comfortable with our tool, all they can do is they can just unscrew this and they can put back the traditional laparoscopic tool what they're using. So hardly this would take 5 minutes, less than 2 minutes in order to do this entire process. That's how we designed this particular one. And before going to this particular design, we went on at least 50 designs, more than 50 designs, and we have a team of surgeons who worked along with us in this particular project, and it was an iteration process, and then we narrowed down to the design. So end of the day, this is the traditional laparoscopic tool. All we wanted to do is we just need to change this side, nothing to do over this side. So that's what we decided. So we came out with many modifications, and at last we came to one of these designs wherein earlier it was only 2 fingers were used, but now what we did is we brought in the idea of putting all the 4 fingers over here. So 3 fingers over here, 1 finger goes here, and the thumb will go inside here, because we need to have an exact navigation which could be only possibly given by the thumb, and that is where we had this region for thumb. And we also gave a projection which fits inside the palm. So ideally we were trying to improve the communication, uh, or reduce the communication error by increasing the surface area of contact. Earlier it was only 2 fingers of point contact. Now we have moved to all the 5 fingers are there, and we have also improved the surface area of contact through this particular segment. And this also started giving power to the surgeons while they need to do the clamping. So this was found to be more effective than the previous scenario. And we 3D printed this particular part using a FDM machine. You could see the printed parts with the actual material and the support material. And once we did that, so this is the final end part that we came out with. And as I have mentioned, so this is how it gets fixed in. So at any point of time, if the surgeon is not comfortable, all they can do is they can just unscrew it and they can go for the traditional one. Whereas if they are comfortable, they can go along with this particular tool. And as I mentioned, this region gets fitted inside the palm. So it gives, so by that way, you'd have more power to do the operation of clamping, which was not there in the previous case. And all the fingers are there in contact, so the surface area of contact is high, and it also reduces the communication error. So this is before and after in terms of the laparoscopic tool. I also discussed about a situation wherein the hand profiles are different. So in order to match the hand profiles and in order to improve the comfort levels for the surgeons, what we did is we came out with yet another option wherein this tool will be constant. Let us say first person would be a female surgeon. So that means her fingers might be very thin. So what we do is for her finger size, we take the hand anthropometric data of that particular surgeon. We print for that particular hand profile, we custom print this insert. This insert goes in here, and we also custom print the insert for the thumb, which goes in here. So that means that for a thin hand, when he or she goes for an operation, all they need to do is it is more like an elastic one. So it is more, so it is like a rubbery one, which is a polyjet printed. So that means that it has flexibility, and we kept a show hardness of 50. So it is neither hard nor very soft. It is somewhere in between. So it gives a very cushioning effect when they tend to do the operation. And on top of it, as it is completely scanned for one particular hand profile, it gives a complete fit for that particular surgeon. So when this surgeon performs, all she need to do is she just need to take these rubber inserts, insert one over here, insert one over here, and she performs the operation. Once she is done with the operation, she can just remove it off. It is just a rubber insert. We have given a groove on both the ends, so it will directly go and sit inside the groove. So when she is performing the operation, she can insert it over here in these grooves, and it gets a tight fit, and she can perform. Once she is done with the operation, and if it is the next surgeon, like, she can remove these inserts and carry on with her, while the other surgeon, he has his set of inserts. You could see for the other surgeon, there is another set of inserts, and he can just go and insert these surgical inserts, and he can perform the operation. So by doing this, what we are doing is we are improving the comfort for the surgeon. So they can just insert these inserts over here and here, and they can perform the surgery. So by doing this, we are improving the comfort for the surgeon, reducing the communication error, and we are also providing the betterment for the patient who is undergoing this particular surgery. And so as a mechanical engineer, we make sure all the notches stands the stresses, possible stresses that it can undergo. And as there is no measure to measure these communication errors, so we can't use any other media to measure it. So we use the qualitative data collection to compare the existing and the newly modified tool, and this is the data of the existing one in terms of how better it was in terms of grip, functionality, comfort, and wrist posture. And we also got a feedback for the modified, the newly developed one. So this is the data which shows the variation, and the newly developed tool is found to be better in terms of performance as compared to the previous one. And so that's a tool, surgical custom tool, custom surgical tool, which was developed for our application. And for in this project, we worked with one of the leading laparoscopic surgical hospital in Coimbatore, and we did happen to work with surgeons on this particular project. And finally, from the academic perspective, we did happen to publish this work in Rapid Prototyping Journal. For further more information, you can just check with this academic paper of how we brought in the ideas. So that is one application which we developed, and this again is another project wherein we worked on a model eye with one of the leading eye hospital across globe, I would say, or one of the very renowned eye hospital. What they do is, as we know, diabetic retinopathy is one of the crucial issue which is popping up, or it is already there. And in order to perform this diabetic retinopathy surgery, generally the surgeons, what they do is they practice and practice for a longer period of time before they go for this diabetic retinopathy surgery. And it doesn't matter if he's a regular periodic surgeon, like if he leaves a gap of 15 days, again he undergoes some practice before performing the surgery. So that's how this particular field is. So they need to have a continuous practice before they go for the surgery. I have a short video which describes about
Hello,
it.
I'm Dr. Jeremiah Brown. You're about to see a video about a specific treatment for your retinal condition to help save your sight. Having any type of treatment or surgery is an important decision to make. To help you decide if this treatment option is right for you, I want you to understand what to expect. This video will explain how the treatment can help preserve your vision. It also explains the possible risks associated with this treatment. Sit back, relax, and watch this video. We'll be happy to explain any questions that you may have about this retina treatment. At the Brown Retina Institute, we are committed to protecting your sight.
When you have diabetes, your body does not use or store sugar properly. This can cause changes in the vessels that carry blood throughout your body, including your eyes. These blood vessel changes can damage your eye's retina, harming your vision. This eye disease is called diabetic retinopathy. Your ophthalmologist has chosen to treat your diabetic eye disease with laser surgery. This treatment can help slow the progression of your diabetic eye disease and save your sight. To understand how diabetic eye disease affects your vision, let's take a look at how the eye works. Light rays enter the eye through the cornea, pupil, and lens. These light rays are focused on the retina, the light-sensitive tissue lining the back of the eye. The retina has two areas: the peripheral retina, which gives us our side or wide-angle vision, and the macula, the small area at the center of the retina. The macula gives us our pinpoint vision, allowing us to see detail clearly. Proliferative diabetic retinopathy, or PDR, is a stage of diabetic eye disease where abnormal blood vessels begin to grow on the surface of the retina. This is called neovascularization. With PDR, many blood vessels in the retina close off, keeping blood from flowing properly to the retina. The retina responds to this problem by trying to grow new blood vessels. However, these new abnormal vessels do not provide proper blood flow. They can also bleed as well as lead to scar tissue, which may cause the retina to wrinkle or even detach from the back of the eye. If similar vessels grow abnormally in the front of the eye, they can block the drainage channels of the eye and cause high pressure and possibly glaucoma. Both your central and side vision can be affected by PDR. Your ophthalmologist has recommended a form of laser treatment called pan-retinal laser photocoagulation, or PRP. It is also known as scatter photocoagulation. This laser treatment helps stop abnormal blood vessels from growing and bleeding. PRP is usually performed in the office and generally takes around 15 minutes. An anesthetic is used to numb your eye, and a special contact lens is placed on your eye to help keep it from moving and to focus the laser. It is important to keep your eyes as still as possible during the treatment. With PRP laser treatment for diabetic eye disease, a laser is targeted at many spots all around the periphery of the retina, avoiding the central macula. Many small burns are made to the retina. This treatment causes the blood vessels to shrink and often prevents them from growing again in the future. It also decreases the chances of blood vessels bleeding. In some cases, multiple laser treatments may be necessary. As with any medication or procedure, there are risks of side effects and complications with PRP laser surgery. These may include temporary pain, decreased night vision, blind spots in your peripheral or side vision, loss of central vision, retinal bleeding, retinal scar tissue, and continued abnormal blood vessel growth or bleeding, which may require additional treatment. Other treatment options may be available for your diabetic retinopathy. Depending on what your ophthalmologist sees in your eye, these options could include medication injection and other surgery. Your ophthalmologist.
Okay, so with that note, like the one thing that we are very clear now is what they do is they pass on a laser light, and that's what they call it as a laser surgery. For people with diabetic retinopathy, you'll find the blood vessels getting opened up, and all they need to do is like they need to bond this. It's more like a building process for us, and this laser light is used to bond these blood vessels, so that by that they remove off the existing blood and they tend to bond these edges wherever there is blood which is leaking out. And for that, this is how a laser surgery is done. You can see that's the laser which is passing, and this doctor is performing the surgery. So we can see that they are performing the surgery in this manner. And in order to perform the surgery, before performing the surgery, um, the doctors, like how for engineers we have certain labs in order to practice uh, before they move out. In the same manner, the doctors, they use mm, a model eye, which is more or less like a surgical experiencing tool. And using that particular tool, they tend to do a simulation, a real-time simulation. They put those model eyes, and then they perform the surgery. So this is a model eye, and inside the model eye, they put a retinal film. This is the retinal film, which is a replica of what is there inside the real eye. They put this retinal eye in, they close this model eye, and closing it, they tend to perform this particular surgery. Yeah, they tend to practice it. And once they are done with the practice, and then they go for the real time. And even a surgeon who is performing the practice, if they have a gap of more than 15 days, then they need to undergo this practice for a couple of hours, and then only they can go for real-time surgery. So that's how for this particular field it works. So understanding this, we thought we'll explore a bit, because there are some intricacies what um, the surgeons said when they were working on this. So looking at the existing design, like what we did is we took the entire design, it's CAD model, and when it is CAD model, this is how it looks like. And looking from the top, you could see that the focal point for them is uh, below the center axis. So anything that they are doing as a practice is below the center axis, but in real life, what happens is when in real life you have an option of flexibility, you can slightly compress this. Um, if you compress it, so that means that the focal point will change. So they can see bit above the central line. Whereas now in practice, they are practicing it below the center axis. But in real life, what happens is they tend to get a vision more than the center axis, because this portion is flexible. So when they press the eye a bit, so they tend to get more focus, the focal point changes. So then we decided it is more of a re-engineering process for us. And this is the system which they use in practice for more than 28 years now. And it is the same system which is followed across globe by different surgeons. So what we did is we came to an option of, or at the end of the day, we redesigned it. If you look at the design, this is the existing design, and we came to a redesign. And in our redesign, you could see earlier it was only this under the below the center axis only they were able to see, but now our redesign, we were able to focus on the same object with a varied covering area, wherein now we are able to see above the center axis. It is more or less very close to what they are doing it in a real time. So we changed this particular one, and the bottom portion we left it as the same. And as I mentioned to you, in Connex, you can print flexible parts. So all we did over here is we redesigned it, and we used a show hardness of 80, which is an assimilated replica of a real eye, wherein our real eye is also a bit flexible. So we showed various samples to the doctors to tell them which is very closest to their real-time application. So from there, we narrowed down to show hardness of 80, and we 3D printed the top portion of it. And this is the comparison between before and after. Before, they were able to see only around 39.08 degrees, but now they are able to see to 41.48. So that is, according to numbers, you would find a deviation of about 2 degrees, but the 2 degrees makes a major deviation when it comes to eye. And now when they are practicing it, they tend to get a wider area of coverage, or a coverage which is very closer to the actual eye. And there they perform the surgical practice. And once they are, as they are having a better vision on the inside process, now they claim that they are able to perform it better. And this is the top portion which we printed for the surgeons, and it is flexible, as I mentioned, and which replicates the real eye. And again, we made sure the tool, the surgical simulation component, it withstands all the mechanical possible loads. And this is the picture when they inserted the retinal film inside the 3D printed part. And this is the time when they perform the surgery. And in terms of cost, with the regular one, they were charged at 2,000 rupees, whereas our 3D printed part with the highest amount of accuracy and longer life duration, it was found to be around 2,526, wherein we are speaking of a slight increase in cost of about 550 close to, but we are seeing of more of an accuracy as compared to whatever it was previous. And again, for this, we can't measure it clearly, so we went through a qualitative data analysis with the various surgeons, and this is the subjective rating that we got in terms of weight, in terms of viewing angle, and the finally 3D printed, the flexible part was found to be far way performing as compared to um, the previous one. And in terms of the entire approach, as the part that we came out as a novel product that was found to be better in terms of application. And now we know that the eye industry have taken off their traditional product, and now they started using this design, whatever we have given to them. So they started using it. And as an academic outcome, we came as an academic outcome wherein this particular work was published in IMECI, Journal of Healthcare Engineering, or Engineering in Medicine. So that was one of our work, and you can see we worked with Arvindai on this particular project. And not only this, then when we were working on this particular project, like what happens is every time they perform the surgery, you could see that they tend to use the surgical tool continuously. I mean, they tend to use a notch-like mechanism wherein they keep pressing it quite very frequently. And this is the mechanism wherein it is a controller which they use in order to perform the surgery. And when they continuously use it, like it tend to go off. This is one lead screw mechanism, one tiny plastic screw mechanism which gets fitted into this. And every time, once in a month, one of their equipment tends to go off. And when one of the equipment goes off, that leads to now they are having roughly about 32 machines of this. If one machine goes off, the entire cost of the machine is quite high, so they need to put it on service. And for the service component, they tend to get it from German, so they need to get this entire kit from German, and then only they tend to go put that one in application. So because of one equipment going down, they tend to have a higher amount of queues, patient queues. So what we did is we took out one of the one out part. We we took the same design of it. We had a design of it, and then we 3D printed the same part, and we started using it for their application. Now that when they go for a change, they need to change this entire kit, which cost them about 15,000. Um, and this is along with 15 days of waiting time, whereas now this part only costs them about 300 rupees when it gets 3D printed. And all they do is they just, you could see that this part has been replaced here. So this part gets replaced, and once the part gets broken, in another 4 hours, the part gets delivered. So there is no queue which tends to happen as what it tends to happen in earlier case. So things move at a bit of faster rate as compared to whatever it was earlier. So that's about this particular project. Um, I know that the time was 10:30. Shall we take a break and then we come back by 11? Would that be fine with you people? Or no, or any questions and whatever we discuss? Because for our next session, I'll go for another presentation of mine. And if there is any question, we'll get it clarified now, and then I'll go ahead with um, the other one. Any questions, please?
Participants, if you are having any queries, just to switch on the mic and you can ask. Sir, then we can
Yes, sir.
take some break and we can come back, sir.
Yes, sir. At what time we are getting back, sir? I'll leave the choice to you, sir.
The schedule time is 11, sir. Is it okay, sir?
Yes, yeah, perfectly fine with me, sir.
Okay, sir. Okay, sir. Okay.
Okay, sir. We'll meet again at 11.
At 11, sir. Okay, sir. Thank you.
Yeah, sure. Thank you.